So now we'll talk about the geometric setting, which is different from the binomial setting in a number of ways. It's not as important ultimately as we move into later units, but it's still something that we need to spend a little bit of time on. So the geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. Then the probability P of success must be the same for each trial. So for example, if a cereal manufacturer has a promotion where they put prizes in 1/5 of their cereal boxes, how long on average would it take us to get one of these prizes? Well, we can calculate that typically it would take the reciprocal of our probability, so 5 over 1, it would take us 5 boxes to get a prize. That is going to be the expected value or the mean of our geometric setting. But we want to figure out what would be the probability, for example, of getting it in the first box, getting it in the second box, getting it in the third box, getting it in the fourth box, the fifth box, etc. Or let's say getting it by the fifth box. That's when we're talking about a geometric distribution. So the random variable, the geometric random variable, we're going to call y, and it's the possible values of y would be 1, 2, 3, etc., which would reflect, for example, y of equal 1 would mean that we got our prize in the first box. Y equals 2 means we got it in the second box. Y equals 3, we got it in the third box, etc. Our parameter p in this case, the probability of success for the cereal situation would be 0.2. Okay, so as we said, Acme Foods is placing a prize in 1 out of every 5 boxes. So we already said that the probability of getting the prize in the first box is just 1 out of 5, 0.2. The probability of not getting the prize until the second box is equal to 4/5 times 1/5, because the probability of not getting the prize in the first box is 1 minus 1/5, or 4/5. So that's where the 4/5 come from. And then we have to multiply that by 1/5, which would be the probability of getting it in the second box. So this would give us 4 over 25, which would give us 0.16 as our probability of getting that prize in exactly the second box that we purchase. Okay, so we're saying that if y equals the number of boxes needed to get the prize, we have the following. The probability of y is equal to 1 is equal to 1 over 5, or 0.2. The probability of y is equal to 2 is equal to 4/5 times 1/5 equals 0.16. The probability of y is equal to 3, which means not getting the prize until the third box. So we would have a 4/5 probability of not getting it in the first, a 4/5 probability of not getting it in the second box, and then a 1/5 probability of getting it in the third box. So overall, when these are multiplied, we would get 0.128 as the probability of not getting the prize until the third box. Now obviously this can go on. There's in fact no end to this because it's possible we would never get the prize. But the probabilities decrease obviously as y increases. So we could also calculate the probability of getting our prize somewhere in the first, second, third, or fourth box, in which case we would sum these probabilities to get a 0.5904, which means that the probability of getting the prize by the fourth box is 59%, 0.5904. Okay, so let's model this more generally. Okay, so let's set our probability, as in the cereal case, to 0.2. And let's say we want to look at the distribution of getting it anywhere in the first 15 boxes. Now, the probability of not getting until the 15th box is going to be very low. So here we look at those probabilities. So the histogram, which is always going to be skewed right, shows that we have a 0.2 probability of getting in the first box, a 0.16 of getting it in the second box, a 0.128 or round to 0.13 of getting in the third box, etc. And that's what this column of values here shows. So the probability of getting it first box 0.2, second box 0.16, third box 0.13, etc. And you can see that the probabilities get very low. Over here in the second column, we have a cumulative distribution function, which shows Now the probability of getting it by the second box, which would be the sum of 0.2 and 0.16, so 0.36. The probability of getting it by the fourth box would be 0.59. And you can see we're now by the 15th box, the probability of getting our prize is up to 0.96. And we can show that histogram looking like this. And you can see that the values get close to 1. Obviously, as the number of trials increases, then our probability by the 24th box rounds to 1. So there's very little chance of not getting the prize by the 24th box that you purchase. So again, this is the distribution function is always going to be right skewed. It's going to look different, obviously, as the probability increases. So when we increase, let's say they were putting these in 2 out of 5 boxes, which would give us a p of 0.4, then you can see that our probability of not getting a prize by the 11th box is basically 0, because the probability of getting it by the 11th box is roughly 1. And then the cumulative distribution function would just climb to 1 more quickly. Okay, so we can also do all this on your graphing calculator. So you go to distributions, the same place that you would find binomial PDF, norm CDF, etc. If you enter geomet PDF 0.2, 2, it will tell you the probability that an event with a probability of 0.2 will occur on the second trial. So this would be the equivalent of saying, what's the probability that we would get our serial prize on exactly the second box that we purchase? Geomet CDF again, cumulative distribution function, 0.2, 2, so the same inputs. Well, now this tells us the probability that an event with a probability of 0.2 will occur on the second trial or earlier. In other words, what's the probability that we will get our prize by the second box? So here's an example. Suppose, for example, that I am checking some electronic parts, and there's an underlying rate of defect of p equals 0.02. If I keep checking parts until I find a defective one, what is the probability that I'll have to check 10 or fewer parts? So we would use, because we're looking for a cumulative distribution here, we would use geomet CDF, or 0.02 and 10 as the number of trials. So the probability is 0.02, which again remains the same for each trial. And we want to see what's the probability that we will get that, find a defective part on or before the 10th one that we check. So this gives us a value of 0.183, which means there is an 18.3% chance that I will find a defective part somewhere within the first 10 that I check.